Hello, space enthusiasts. Are you ready to dive into some of the most thrilling advancements in space technology and exploration? Today, we're exploring three groundbreaking topics: telescopes shooting lasers, assembling telescopes in space, and growing plants on Mars. So buckle up as we journey through these incredible innovations that might just reshape our future in the cosmos. Each week, we'll be bringing you a curated collection of intriguing questions from last year. Today's episode features gems from our shows in September and October of 2023. Sit back and enjoy as we unravel some of the universe's most captivating mysteries. First up, a surprising botany question from Horizon Brave. If we bring back samples from Mars, could we plant Earth seedlings in Martian soil? Given that the nutrients would be completely different, this is a real challenge. So far, we haven't grown plants in Martian regolith because we've never retrieved samples from the red planet. However, we've experimented with lunar soil plants sprouted but quickly perished, as lunar regolith lacks the nutrients they need to survive. When the Mars sample return mission finally brings back Martian soil, scientists will undoubtedly experiment with planting in this alien regolith. But without the necessary adjustments, these first botanical pioneers are predicted to sprout and then sadly perish, much like their lunar counterparts. Remember the movie The Martian? The hero, stranded on the red planet, ingeniously grows potatoes using the only organic material available: human waste. This isn't just Hollywood magic. It's a critical lesson in space agriculture. Plants need organic materials and microbial life to thrive, which Martian soil naturally lacks. As we dream of Martian farms, we face the challenge of transporting and establishing a robust microbiome bacteria and fungi that can support plant life. This will be a vital step in transforming the barren Martian landscape into a place where astronauts can actually farm and sustain life. So, as we gear up for future missions, one of the biggest hurdles will be creating a viable ecosystem from scratch, making Mars a little more like home. Now, shifting our gaze to Earth, let's talk about those mesmerizing lights at the Mauna Kea observatories. Ever wondered about that bright laser shooting skyward from the telescopes? That's part of an incredible technology known as adaptive optics. Here's how it works. When you're on the big island of Hawaii, looking up at the night sky, you might catch the observatories actively observing the cosmos. They use a high-powered laser to project an artificial star into the heavens. This serves as a stable reference point for the telescope systems. But why an artificial star? It's all about precision. The telescope needs a known point of light to measure distortions in its view caused by Earth's atmosphere. When the telescope detects that the artificial star appears blurred rather than a sharp dot, it automatically adjusts the shape of its mirror. This adjustment compensates for atmospheric distortions, bringing celestial objects into sharp focus. Let's take a closer look at this fascinating process. Beneath the gigantic mirrors of the world's most powerful telescopes, like those on Mauna Kea, lie intricate arrays of pistons. These aren't just any pistons, they perform a delicate dance, subtly deforming to reshape the mirror in real time. This incredible engineering feat is all in service of capturing a clearer glimpse of the universe. The system starts by shooting a laser into the night sky to create an artificial star. Why do we need this folk celestial body? It acts as a benchmark to measure atmospheric distortions that blur our view of space. If the artificial star appears as a distorted blob rather than a crisp dot, the pistons spring into action, tweaking the mirror's shape until the star sharpens into perfect focus. But wait, it gets even more futuristic. While telescopes like those on Mauna Kea use one laser, the upcoming extremely large telescope steps up the game with not one, but 4 lasers. Picture this: 4 turbo lasers firing into the night, each adjusting the telescope's focus across different parts of the sky. This multi-laser strategy allows the telescope to manage atmospheric disturbances across a wider field of view, maintaining crystal clear focus throughout. This technology isn't just improving, it's revolutionizing our ability to peer deeper into the cosmos, effectively making Earth's pesky atmosphere disappear It's a game changer for astronomers, providing them unprecedented clarity to explore the mysteries of the universe. But then came a game-changing breakthrough in the 1980s, adaptive optics. This revolutionary technology peeled back the atmospheric veil that had long clouded our view, unlocking the true potential of ground-based telescopes. Now, the sky is literally the limit. The larger the telescope, the clearer and more detailed the view of the universe it can provide. Take the extremely large telescope, for instance. This behemoth isn't just big. It's equipped with technology that will allow us to observe Earth-sized planets orbiting stars light years away, right from here on the surface of our own planet. Thanks to adaptive optics and other advanced instruments like the coronagraph, we're on the brink of peering into distant worlds with unprecedented clarity. And yes, if you ever find yourself gazing up at the observatories, you might just see the cool spectacle of a laser streaking into the sky, a visible sign of the technology at work. Now you might wonder, why haven't we built an ultra-large modular space telescope that's assembled right in space? The idea has merit, and frankly, it feels like we're overdue for such an innovation in space-based observation. About 5 years ago, I reported on a fascinating proposal from NASA, the idea of building a space telescope directly in orbit. Picture this: instead of launching a massive telescope in one go, which is nearly impossible due to size constraints, we could assemble it in space piece by piece. Here's how it might work. You start with the core hub of the telescope, complete with onboard intelligence and a few robotic arms. This central module would be launched into space and positioned at its future location. Once in place, it could receive and attach solar panels, followed by segments of the primary mirror. The robot arms would carefully piece together the mirror and align all the components to build a telescope of virtually any size right in space. This assembly method mirrors the approach used for the International Space Station, which was constructed in orbit from various launched modules. NASA is seriously considering this innovative idea, though it's still in the concept stage and comes with its own set of technical challenges. If successful, it could revolutionize space observation by allowing for the creation of telescopes far beyond the size limitations of Earth-bound launches. Now, let's shift gears to the James Webb Space Telescope, JWST. If it were to suddenly break down tomorrow, would we have gotten our money's worth? The answer is a resounding no. While JWST has made incredible strides and is beginning to unveil the mysteries of galaxy formation and the early universe, it's still deepening the enigma rather than solving it. We need more time and more data to fully appreciate its value. By the end of its first decade, JWST is expected to deliver profound insights and possibly resolve some of the cosmic puzzles it's currently exploring. Until then, its journey is far from complete, and its ultimate worth remains a work in progress. Now, about carbon nanotubes and space elevators, there haven't been major updates recently. A dedicated group, like the Liftport Society, continues to discuss and explore the potential of space elevators. Meanwhile, we're seeing the rise of fully reusable rockets like SpaceX's Starship, which are becoming competitive in terms of cost with the idea of space elevators. However, space elevators still face significant challenges. They can't carry as much cargo as these massive rockets, and we're still struggling with the materials. Carbon nanotubes are theoretically strong enough, like electromagnetic launchers, essentially giant railguns, or even a space elevator. The concept of a space elevator sounds like science fiction, but it comes with a host of challenges. How do you power the system? How do you build the massive structure? And what about the materials needed? These issues remain unsolved, making the space elevator a distant dream for now. Enter the revolution of two-stage rocket systems, like SpaceX's Starship. In theory, this innovation could slash the cost of reaching space by a staggering amount. Currently, sending a payload into space costs around $3,000 per kilogram on a Falcon rocket, and it was once as high as $110,000 per kilogram on the Space Shuttle. Starship aims to bring that down to just $100 per kilogram. If Starship lives up to its promises, it could make space access far more affordable and transform our ability to explore and utilize space. One of the biggest hurdles is providing the enormous amount of electricity needed to operate the elevator. Imagine trying to power a system that has to transport payloads up and down a massive cable. Adding more elevators means even more electricity, and powering them with solar panels could take weeks to reach the top. Meanwhile, a rocket like SpaceX's Starship can make the trip to geosynchronous orbit in just a few hours. Space elevators were envisioned in an era when we couldn't conceive of more efficient methods for large-scale space travel. They represented the grand ambition of getting off Earth on a massive scale. Today, however, with advancements like fully reusable rockets making space access more affordable and practical, the need for space elevators has diminished. The market opportunity for space elevators is shrinking as rockets become increasingly cost-effective. While space elevators may still be a fascinating concept, their economic viability is waning in the face of more efficient alternatives. Why? Because the technology required is out of this world. First, we need a laser far more powerful than anything we've ever built. Then, there's the challenge of creating a solar sail from a material that's not yet developed. Plus, the spacecraft itself needs to be something we've never engineered before. We're talking about massive technical hurdles, and while none of them seem insurmountable, solving these problems is taking time. It's been nearly a decade since Breakthrough Starshot was first proposed, and progress has been slow. There have been some advancements, new solar sail projects have emerged, and lasers have become more powerful thanks to efforts like the National Ignition Facility. But despite these strides, we're still a long way from making Breakthrough Starshot a reality in the next 20 years. The idea remains a thrilling glimpse into what could be, but it will take more time and innovation before we can set sail for the stars. Here's the vision. A tiny probe equipped with a solar sail, propelled by powerful lasers, could zoom across the solar system at nearly 10% of the speed of light. Picture this probe reaching Ceres in just a few hours, sending back stunning images of its surface. You could launch thousands of these probes to explore asteroids, capture detailed photos, and share them with us back on Earth. The possibilities are thrilling, sending probes to Neptune to explore its moons, visiting the distant planet Sedna, or even using a solar gravitational lens to peer deeper into the cosmos. The list of potential destinations is endless. As we refine this technology, overcoming challenges like laser power requirements, sail size, and communication protocols, we'll gain a deeper understanding of its capabilities. But the exciting part is seeing this groundbreaking tech push the boundaries of space exploration and bring new worlds into our view. Now, moving on to an intriguing question from Evolving a P, how big would a black hole be with 1/100th of the gravity of Earth? And how close could you get to it without being spaghettified? To give you an idea, a black hole with the mass of Earth would have an event horizon about a centimeter across. If we scale that down, a black hole with 1/100th of Earth's gravity would be even smaller, perhaps just a fraction of a millimeter. As for how close you could get without experiencing the extreme tidal forces that cause spaghettification, the answer is pretty close. The gravity of such a tiny black hole would be similar to that of a small asteroid. You'd only feel significant tidal forces when you were practically in contact with it. So, you could approach very closely before feeling those intense gravitational pulls. Now, onto another fascinating topic from Ceres K. Lee. Could the Gemini North and Gemini South telescopes work together to perform optical interferometry? Unfortunately, no. Optical interferometry, like what we see with the Event Horizon Telescope, EHT involves radio telescopes around the globe working together to simulate a telescope the size of Earth. It's a mind-blowing concept. But when it comes to optical interferometry, things get trickier. The Very Large Telescope, VLT in Chile, achieves this feat with its 4 main telescopes and 4 smaller ones, working together in near-infrared light. They do this by precisely measuring the interference of light on sight, knowing the exact distances between the telescopes. This requires extremely accurate timing and positioning, which is much harder to achieve over the vast distances separating the Gemini North and South telescopes. So, while the idea is captivating, the technical challenges currently keep us from using widely separated optical telescopes in the same way as the EHT. The challenge lies in aligning the two telescopes down to the nanometer scale. While the idea of an interferometer that large is intriguing, it's beyond our current capabilities. However, there is a silver lining. The Gemini North and South telescopes can still collaborate by observing the same object simultaneously. By combining their data, we could effectively create a telescope with double the size of either Gemini telescope on its own, though not matching the vast distance between them. This additive approach enhances the observational power, but doesn't achieve the same level of resolution as an interferometer. For a truly powerful interferometer, we'll likely have to look to space. Projects like LISA Laser Interferometer Space Antenna are paving the way, using lasers to maintain precise measurements and balance in the vastness of space. LISA aims to detect gravitational waves, showcasing the incredible potential of space-based interferometry. Europa is one of the most exciting destinations in our solar system. This moon of Jupiter is fascinating because tidal forces generate enough heat to maintain a liquid ocean beneath its thick ice shell. There's strong evidence suggesting geological activity on Europa, similar to its neighbor Io, which is the most volcanically active body in the solar system. This means Europa likely has underwater volcanic activity, providing nutrients to its ocean. It has all the essential ingredients for life: water, heat, and nutrients. Future missions, like NASA's Europa Clipper, aim to explore this enigmatic moon further. They'll look for signs of this geological activity, analyze the ice, and search for potential signs of life in the ocean below. For me, the most thrilling aspect of Europa is the possibility of discovering extraterrestrial life. If life can exist in Europa's harsh environment, it could mean life is more common in the universe than we thought. Have you ever wondered how astronomers refine their view of the distant cosmos? One answer lies in the use of powerful lasers shot from ground-based telescopes. These lasers create artificial guide stars in the Earth's upper atmosphere, which help telescopes correct for atmospheric distortions. This technique, known as adaptive optics, allows for sharper images of the universe, enhancing our understanding of space's vast expanses and mysteries. Welcome to Blesovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blesovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blesovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.